Lesson 6. Up until now, lessons 1 through 5, I've been really trying to drum into your head this notion of Newton's 3 laws, a free body diagram, and then our approach, which is using a tug of war, winner minus loser equals ma, the net force, F net. Today, Physics 12 begins. We say, hey, what if stuff's on an angle? Did I say angle? Yes, you might be thinking components and trig, which, yes. But we're going to try and go systematically. And Jordan, what we're going to try and do is use the same method over and over. You may notice I have a fondness for saying, hey, here's how you can start, and we can adapt it to anything out there, as opposed to memorizing every possible diagram under the sun. I'm not going to do that. So here's our first little thought experiment. A person is on a ramp, and they're standing on a scale that measures in newtons, attached to a rope. As the angle of the ramp increases, what happens to the scale reading? A, no change. B, increases. C, decreases. Leonard.
C.
Decreases?
Yeah.
Convince me.
Because he's attached to the rope, and when the angle is getting bigger and bigger, he's getting caught by the rope and not anymore standing on the scale. And when you have 90 degrees, he's hanging.
Your explanation is right.
Yeah.
Too much writing. So I'm going to, first of all, it does decrease. So one of the things I'm trying to do at the beginning of the year here, Colin, is give you various tools in your toolbox to analyze physics. Free body diagram, making up reasonable numbers. We did that a bit last unit. Here, another strategy is looking at the extremes. So I'm going to call this angle here angle theta. And what are the two extremes? Theta can be 0 degrees. Theta can be 90 degrees. I can imagine both of those. And then I can say, well, it's got to get from one to the other smoothly. So explain your answer. I'm going to draw the line. And I'm going to say, if theta equals 0 degrees, what would the normal force read? Ah. It'd be your standard. Get the obvious one, look, and another force the same size as the normal force. What if it was vertical? He'd be hanging from the rope. This is what Leonard was trying to allude to. If he's hanging from the rope, what's the scale reading? 0. So if theta equals 90 degrees, if you go from a normal force of mg to a normal force of 0, are you getting bigger or getting smaller? I think 0 is getting smaller, decreases. Then I would say, therefore, because it has to do it smoothly. It wouldn't magically get bigger, get bigger, get bigger, get bigger. Boom, now we're 0, huh? That's not how physics works. I think we can use a very similar approach for the next question. So if we consider the person in example 2, as theta increases, what happens to the tension in the rope? Rob,
increases.
Convince me.
Because as the normal force closes to 0, then the weight must be acting.
Sure.
Yeah.
Let's write this succinctly.
Yeah.
You know what? Let's use our trick again of looking at the extremes, because almost always the extremes, 0 and 90, or for whatever situation I throw at you, think about the biggest and the smallest. Those are often one we can obviously easily come up with. So I'm going to say if theta is 0 degrees and if theta is 90 degrees, if everything was flat, I think the rope would actually have some slack, which suggests that the tension is what?
0.
Ah. If you're vertical and now you're hanging from the rope, what does the tension equal? mg. How would you go from 0 to mg? I guess that's increasing. You know what? Here's my abbreviation for decreasing and increasing. I'm even going to do it up here. You don't need to. But therefore, decreases. Therefore, increases. I'm good with that. You may have noticed I tend to abbreviate. Okay. I'd figure out what you meant. And also, I like to do no English word answers because that way it works for my ESL students, but it would work if I showed this to somebody from a different country. They'd figure it out. So what we're noticing then is as the angle gets higher, normal force gets smaller, which would also mean friction force gets smaller since friction is mu times the normal force. What this shows is that for objects on a ramp, the force of gravity partly pulls the mass into the ramp and partly pulls the mass down the ramp. And how big each of those parts is, Quinn, depends on your angle. If you're at 90 degrees, all of gravity is pulling you down the ramp. Nothing's pulling you into the ramp. If you're at 0 degrees, all of gravity is pulling you into the ramp. Nothing's pulling you along the ramp. If we were going to draw a free body diagram, or you know what, if we were going to label our forces, we would say, get the obvious one. What is the obvious one? Gravity. Draw it nice and big for a reason. And put mg on the right of the arrow for a reason. By the way, when you draw it, you want to put mg on the same side as the pointy part of the ramp. Trust me. What we're going to do is we're going to break this up into components. What kind of components? We're going to say that this is made up of a perpendicular component and a parallel component with a lovely right angle there. Let me zoom in so you can see this even more. We're always going to break gravity up into squeezing into the ramp and sliding down the ramp. Parallel and perpendicular. And I'm going to label these as follows. I'm going to call this mg. Hey, is there a symbol for perpendicular? Turns out there is. Does anybody know what the perpendicular symbol in geometry is? It's an upside down capital T. It's two lines at a right angle. And I'm going to label this one as mg. There's a symbol for parallel. Does anybody know what the symbol for parallel is? Okay, by the way, I can't use P and P because perpendicular and parallel both begin with letter P. So I got to go to geometry symbols. Symbol for parallel, two slanty parallel lines. This is what's happening on every ramp. On every ramp, there's two components to gravity. Part of gravity is keeping you on the ramp by sucking you into the ramp. Part of gravity is pulling you along the ramp. The steeper the ramp, the more you're getting pulled along, the less you're getting pulled in. That's why the steeper the ramp, the lousier our balance is, the more we feel like we're going to slide. So, in terms of other forces on the ramp, that act on the object on the ramp, there will be a normal force. Oh, let's see. What are the forces acting on this mass? Get the obvious one. Gravity. And then I'll break it up into components. Now, is this mass sinking into the ramp like quicksand? Is it flying off the ramp like Superman? So the normal force is going to be the same size as mg perpendicular. It's going to be, oh, but look. I know another force the same size as the normal force, but it ain't mg. It's the perpendicular component. Because that's how hard the surface has to push up. And again, that's why as you get totally vertical, now the surface doesn't have to push up at all. The normal force is 0. What's pulling you down the ramp would be that one there. In fact, if this was your free body diagram, if all you had was normal force and mg, you have forces balanced into the ramp, but you would have to be sliding, accelerating down the ramp because there's nothing counteracting gravity. What if you were wearing really good shoes that were sticky? Friction would be acting up the ramp. And you know how big friction would be? Exactly that big. Let's actually do the question. It says, draw a force diagram for an object on a rough ramp that is sliding down the ramp. Okay. Rough, what that means is there's a mu, there's friction. What are the forces acting on this here block? Get the obvious one. Gravity, straight down, draw it big. And trust me, you're going to want to put mg on the same side as the pointy part. I don't like gravity. I'm going to break it up into components. I'm going to break it up into a perpendicular component and a parallel component. I want you to notice, this is very important because this is one of the most common mistakes. The parallel component is parallel to the ramp. Here's what I see some kids do. Don't write this down. This is wrong. I see some kids, they get gravity, great. And then they go, okay, they want to make parallel to the ground. You're going to get all the wrong stuff. Okay? So don't do it that way. Instead, it's going to be, and I'm doing it as a dotted line because it's a component. It's not a second force. It is still gravity, so I don't want to do a solid. You can, but I'm not going to do a solid line because that would suggest there was an extra force. Here's the perpendicular. Here's the parallel. And where is the right angle? Right there. But it is a right angle, which means sine law, cosine law? No. SOHCAHTOA and Pythagoras. Which way are we sliding? Which way would friction be acting then? Friction, which I'll do as a solid line. Oh, first of all, is this sinking into the ground like quicksand, into the ramp like quicksand? Is it flying off the ramp like Superman? Then you know what? There is a normal force, and it's exactly the same size as mg perpendicular. And if you're sliding down the ramp, friction must be acting up the ramp, but friction, since you are sliding down, has to be smaller than what's making you slide down the ramp. Which force is making you slide down the ramp? Not mg, I gotta be fussy. Which force is making you slide down the ramp? mg parallel. So here would be friction smaller than mg parallel. The three blue forces would be the free body diagram. The red line, dotted line, that would be what I would add if they wanted me to solve it. Compare that with sliding up the ramp. Now someone might say, Mr. Dewick, how can you be sliding up the ramp? I'll show you real quick. So no applied force, which means what are the forces acting on this block? Get the obvious one. Why do you draw gravity so big, Mr. Dewick? So I can do a nice easy triangle to read. So I tend to really draw gravity big. Also because I know mg isn't going to have something canceling out. It's going to be components. I'm going to break it up into mg perpendicular and mg parallel. I'll put my lovely little right angle there. Is this block sinking into the ground like quicksand? Kind of looks like it is. That's because I suck at drawing these. Is this block sinking into the ramp like quicksand? Let's pretend it's not. I couldn't get this little corner to line up to save my life, and I gave up after a while. So is it flying into the air like Superman? You know what? There has to be an equally sized force to mg perpendicular. Did I draw that a little long? I think I drew that a little bit long, didn't I? From here to here, probably about like that. That looks better. What else? Is there friction? Yes. Which way is this block sliding? So which way is friction acting? And this is why it's going to slow down really fast, because not only is gravity parallel slowing it down, friction is also slowing it down. What about, let's go back to this situation right here. What if you're at rest? The way you're at rest, if you've ever stood on a slant and kept your balance, what really happens is gravity is pulling you down and the friction force is exactly the same size as mg parallel. That's what at rest means on a slope. By the way, as the angle gets bigger, what happens to the normal force? What did we just say? Gets bigger, smaller, or stays the same? Smaller. What happens to friction? Because friction is mu times the. That's why as something gets steeper, it gets harder and harder for you to keep your balance, and eventually there's a magic angle where you'll start to slide down. Okay? Which of the following is the best force diagram for a mass that is at rest on the ramp? You know what? I would underline the word at rest because that's the key to this question. Which of the following is the best force diagram for a mass that is at rest? A or B? And convince me. Leonard.
A, because we need friction to be addressed.
Okay. If B was right, and I broke gravity up into its components, are the forces into the ramp balanced? Yeah. Are the forces down the ramp balanced? This must be accelerating. Can't be that. Whereas if I break gravity up into its components here, these two are canceling each other out, and these two are canceling each other out. That can be either at rest or it could be at a constant speed because all it tells me is that my acceleration is 0. But this question said at rest, so I know it's at rest. Is that okay? As an explanation, I would probably draw that, and then I would just say, really what you use is Newton's first law. You said, oh, forces have to be balanced for it to be an acceleration of 0 at rest. Now, we haven't yet, Cade, gone into the, oh, I should circle A. We haven't yet gone into the actual trig. I'm going to recommend, just for our own sanity, that we all decide we're all going to make our diagrams look the same. You see, I am always, when I draw gravity, I am always going to do the perpendicular and the parallel first. You could, if you wanted to, you could, here's a ramp. You could say, here's gravity. You could go parallel and then perpendicular. I'm just going to say, Jake, don't, just so all of our diagrams look identical. And then we can memorize a couple of shortcuts. So here's what it says. Example 5. In order to determine the size of the squeeze and slide components, we need to find the angle. I'm going to walk through this proof once, and then we're just going to memorize where the angle is because it's a tiring proof. So it says, complete the proof below to show that the angle is always, this angle right here, is always equal to this angle. Okay, let's see if we can. How big is angle 1? Why? Because perpendicular. Gravity goes straight down. How big is angle 2? I'm going to argue that angle 2 is 90 degrees minus angle 1. Because what does every triangle have to add to? Sorry, minus theta. Because what does every triangle have to add to? 180. And if this angle is 90, then I have 90 degrees to play with for those guys. Is that okay? So triangle equals 180. If you want to be fussy, in English we call this the angle sum of triangles rule. How big is angle 3? See a Z? I think we've seen this earlier this year. How big is angle 3? It's the same size as? Why? Well, it's called alternate interior angles. You can write down Z rule or whatever, but okay. So how big is angle 4? Well, if angle 2 is the same as angle 3, and angle 3 is 90 minus theta, and this angle here is 90 degrees, doesn't angle 4 have to be the same size as theta for that to work? In other words, in this triangle, theta plus 90 plus angle 2 adds to 180. In this triangle, 90 plus angle 2, because angle 3 is angle 2, plus, oh, that must be theta to add to 180. This angle up here is always going to be this angle here. And the way I'm going to choose to show that, Jose, is I'm going to go color, color, scribble, color, color, scribble. That's going to be my high-tech way of showing those two angles are the same. Now let's get tricky with it. Let's do an actual question. Example 6, I like example 6, I like example 6, I like example 6, except example 6 is even a little easy because there's no friction, but we're going to start here. It says, find the acceleration of a 2 kilogram mass sliding down a frictionless 25-degree angle ramp. You know what this is a job for? Free body diagram. Oh, you know what? Instead of a separate free body diagram, let's just label the diagram that they gave us. What are the forces acting on this 2 kilogram mass? Get the obvious one. Let's draw gravity in, nice and big. And I'm going to put the mg on the same side as the pointy part, trust me. I told you from now on, I'm always going to go perpendicular, then parallel. I'm going to break gravity up into perpendicular and then parallel. I'm going to put a lovely little right angle symbol here. I'm going to go mg perpendicular, and I'm going to go mg parallel. And, Jake, here's the next thing. See this 25 degrees right here? It's that 25 degrees right there. And I just do a little scribble to remind myself those two angles are the same. Is that it? No. Is this ramp sinking into the ground like quicksand? Into the ramp like quicksand? Sorry, let's try that again. Is this block sinking into the ramp like quicksand? Is it flying here like Superman? So perpendicular to the ramp, forces must be balanced, which must mean that there is a normal force. Is there friction? Meh. If there was, which way is this block sliding? Down, I'd have friction pointing up. No friction. This is it. Here's my free body diagram. This thing's really going to slide fast. It's like, this is bobsledding, going down an icy hill. Okay. Which way is this thing accelerating? What direction? Down the ramp. Yes? So here's my question. Who's winning? Don't say mg. Mg parallel. Down the ramp. Who's losing? Anything that was pointing up the ramp. Is anything pointing up the ramp? So my equation here is going to be winner, no loser, equals ma. Let's look at this triangle that we've drawn. Tyler, here's my angle right here. mg parallel, opposite, adjacent, or hypotenuse? The one that I do know is mg, adjacent or hypotenuse. Which trig function? O and H? Sine. Okay? So if I was doing the trig, I would say sine theta, I'll do a generic one, I know theta is 25 degrees, equals opposite over hypotenuse. By the way, some of you are noticing, I know masses and stuff cancel. I'll do that a bit later. I just want to do a generalization here. How would I get the mg parallel by itself? What would I do with that mg that's on the bottom? How could I move it over to the other side? So if I hear you correctly, here is our generalized expressions. I never had a good way to, by the way, I showed you how to derive it, but we're going to use this so often, this is going to be one of the things we're going to memorize. I never had a good dumb way to have this memorized. 2 years ago, one of my students said, hey, Mr. Duick, mg 2 lines is sine. I went, oh, okay. So mg parallel, which is 2 lines, is sine. In other words, this is going to be mg sine theta equals ma. Now, is there an m in everything on the left? Is there an m in everything on the right? Turns out, mass cancels. Mass in this question with no friction is irrelevant. And this explains why when we ski, a grown-up can ski with a little kid without having to constantly adjust their speed because the mass cancels. A grown-up and a little kid can ski next to each other, and the grown-up isn't always having to dig in their skis and slow down, always having to dig in their skis and slow down. What's G? Not negative. We took care of that in our winter minus list. Sine 25 equals A. Okay. What is the acceleration in meters per second squared? Crunch it on your calculator. Oh, also, Math 12s, make sure you're in degrees and not radians, right? We haven't done trig for a bit. Yeah, 4.14? I'll go 3 sig figs. 4.14 what? Now, just to convince ourselves, Jake, that this is right, if this ramp got steeper, would you accelerate faster or slower? You know what? Steeper would mean a bigger angle. I'm just going to try going, instead of 25 degrees, I'll try 65 degrees. If my method is right, should I get a bigger acceleration or a smaller acceleration? Bigger, right? Okay, I think I've convinced myself. Oh, if it was 90 degrees, what should my acceleration be? G. Let's see that. You know what? Let's try going, just because if this works, then this really convinces me that my method is right. So you're telling me if I put a 90-degree angle in, I'm in free fall? Am I? Oh, okay. I think we're good. Did I ask anything else? Nope. There you go. So MG parallel, if you draw the diagram right, MG parallel 2 lines will be sine. And it'll be that every time. Take a guess, by the way, if MG 2 lines is sine, what do you think MG perpendicular is going to be? Of course it is. Okay? There's a reason why I did that stupid joke a while ago, but it's really for this, because we're going to be flogging this to death. Ooh, now we got friction, example 7. I think I said I like example 6. I really don't. I like example 7. I like example 7. I like example 7. Example 7 is a nice question. Although, you know what? Once we find the acceleration, I could even give you an initial velocity, a distance, and say find the final velocity, or find the time, or all the stuff that we did from the last unit. Example 7 says, consider a 5-kilogram mass sliding down a rough ramp. Find the force of friction, find the acceleration. We're actually going to find the force of friction, but then we're going to pretend we haven't. We're going to find the acceleration from scratch just to show you how I would do it in one fell swoop. But how are we going to start? Label the forces. Get the obvious one. Yes. Hopefully the method to my madness is now starting to become a little clearer now that we're getting to more complicated diagrams. I'm going to draw a big gravity. Where am I going to put the mg? By the way, do you notice why I always put the mg on the pointy side? Otherwise, the mg is going to be inside my triangle, and I won't know which side it belongs to. Isn't that clever? So I'm always going to put the mg on the pointy side. And I'm going to, is there a ramp? Components. I'm going to break mg up into mg perpendicular, mg parallel. Oh, and you know what else, Tyler? I'm going to go color, 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 color. That's the 35-degree angle there. We proved it once. We won't prove it again. What else? Is this mass sinking into the ramp like quicksand? Is it flying into the air like Superman? So that means there must be this force in this direction. There has to be a normal force. Which way is this mass sliding, up or down? Which way is friction acting then? I got to be careful, up the ramp, right? Not up, but up the ramp. And I should have said, which way is this mass sliding, up the ramp or down the ramp? So friction, why did I draw friction shorter than mg parallel? Because I think mg parallel is winning. Okay. By the way, if I just asked you for the free body diagram, the 3 blue forces are what I'd be looking for. I didn't ask you for the free body diagram. I said solve. Okay. What's the first thing it wants me to find? Jose, what's the first thing it wants me to find? Oh, friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force, and it ain't mg! This is why I tried to drum that out of you. Jordan, what'd you say? mg perpendicular. So if I hear you correctly, you're saying friction is mu mg perpendicular. Which trig function is mg perpendicular? Well, if you wanted to walk through it, you would notice that it's adjacent, that it's hypotenuse. Tyler, which trig function would that be? Cosine. Or you can just say mg two lines is sine. What's going to be perpendicular? Well, of course it is. Okay. That would be the generic expression. But they did tell me what theta is. Theta is 35. Now I'll plug in numbers. So the force of friction is going to be, what's mu? I don't know. What's mu with you? What's mu? 0.2. Notice now mass makes a difference with friction. G, 9.8, not negative. Cosine of 35. How big is the force of friction? What? 0.2 times 5 times 9.8 times cos 35. You get 8.03? 8.03 what? Newtons. Is that right? Yeah, okay. Put a box around it since that's my answer. B. Fayez, what's B asking me to find? Oh. Okay. We've done this before, not at this level, but to find acceleration with forces. Oh, I asked myself, who's winning? Who's winning? mg parallel. So anything that ends up pointing, which way is the ramp for you guys? This way. Down the ramp will be winner plus. Anything that ends up pointing up the ramp will be loser minus. Anything that's perpendicular to the ramp ain't going to show up in my equation immediately. Might later, but not right now. Who's winning? mg parallel. Is there a loser? Yep. Friction. That equals my net force, and my net force is always just plain old ma. Now, I know we calculated what friction was, but I want to do this algebraically so you can see a lovely little generic equation first. So now on my next line, I would say mg parallel minus friction is what times what? Mu times, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. So it would be mu mg perpendicular equals ma. Those of you that are particularly astute might already notice, I think the masses are going to cancel. We'll cancel them in just a second. Mg parallel, which trig function was that? Oh, 2 lines of sine. Okay. So mg sine theta, I know it's 35, but I'm doing a nice generic one, minus mu mg perpendicular. What was that? Oh, of course it was. Is there an m in this term? Is there an m in this term? Is there an m in this term? Tyler, is there an m in every single term? Then you know what? Turns out I could have given you this question without the mass. Part B. Part A, we needed the mass to find the force friction. You know what? Even when there's friction, because there is some friction on snow, a grown-up can ski with a little kid without having to adjust their speed all the time. The mass is irrelevant. Kind of cool. So we have g sine theta minus mu g cos theta equals a. There's our generic algebraic expression. Oh, what's g? 9.8. Sine theta is 35? Minus, what's mu? I don't know. What's mu with you? 0.2? 9.8 cos 35? You know what? If you have a good calculator, this should be fairly easy for you to just type in one fell swoop. 4.01? No, 4.02, if I round off properly, yes? Yeah, someone else get that? Yeah, okay. A equals 4.02 meters per second squared. And now, Jake, that we have the acceleration, you know what, as a nice follow-up question, I might say, oh, if you slide for 8 seconds, how far do you slide? Or also, like all the stuff from Unit 1, all the kinematic stuff to me is now fair game as well. Okay. By the way, on a ramp, when it's vertical, what's your acceleration going to be? More specific as a number. 9.8. When it's flat, what's your acceleration going to be? 0. If you're finding the acceleration on a ramp and you get an answer that isn't between 0 and 9.8, I guarantee you've made a calculator mistake or done something wrong. So there's also a little built-in error check. I know I'm not going to go faster than 9.8 down a ramp. And if I get a negative, oh, you know what? I probably have the wrong winner. Ah, something else is bigger. Friction was bigger. I'm slowing down, maybe, or something like that. How many more am I doing here? 2 more? Okay, we can get this done. Example, oh, I know, because we did the science demo. That's why this one went a little longer, because that took 10 minutes. A 7.5 kilogram block remains motionless on a surface that is inclined at an angle of 21 degrees. What is the minimum coefficient of friction on the surface? You know what I'm going to do here? What does DULP stand for? I'm going to draw a picture. Okay? Just so all of our pictures look the same, let's have the pointy part of the ramp pointing to the right. You don't have to, but so I'm going to go like this. There's my ramp. Mr. Duick, you're really ramping things up this lesson. I almost mark these jokes in my calendar because they're so bad. They almost... Anyway, okay. 21 degrees right here. And here's the block. I'll change colors now. What are the forces acting on this block? By the way, if I was going to give you... If you are drawing a picture, you want to get this wrong, here's how you get this wrong. If you draw a small picture, you're going to get it wrong. Because you can't, if you draw a fairly big picture, the answers look roughly to scale with your lines, and you have a gut instinct for whether an answer should be bigger or smaller or the same size. It's a little bit of advice. That's why there's a reason I gave you a whole page for this, yeah? Yeah, lots of room. The only reason I didn't make my picture bigger is I want to try and fit all this on one screen. What are the forces acting on this block? Get the obvious one. Yoink. Mr. Duick, you went all the way past the ramp. Yeah, I want to do a nice big triangle. It's easy to see. I don't care. And I'll put the mg on the same side as the pointy part. Is there a ramp? Components. I'm going to break gravity up into mg perpendicular and mg parallel. Is this mass sinking into the ramp like quicksand? Is it flying into the air like Superman? So there has to be perpendicular to the ramp another force. How big? Bigger, 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 bigger. About that big, yeah? Which way is this ramp, which way is this block moving? Oh, it's not. So which way must friction be acting? It's got to be up the ramp. Otherwise, I'd have unbalanced forces and it would have to be going down the ramp. So friction. Why did I draw friction exactly that long, by the way? I may as well make my, yeah, I'm pretty sure it's a tie. It's going to be the same as mg parallel. I may as well make my picture look nice. Friction. Who's winning? It's a tie. But you know what? Let's suppose, Tyler, you missed that. Let's suppose you said, well, it's a ramp. I think mg parallel's winning. Okay, we would go like this. Winner. Friction is clearly a loser because it's pointing up the ramp. Yes? Don't write this down, just watch. But what if you're not moving, what's the acceleration? So what's mass times 0? Although, how would I get the friction by itself? Since there's a minus in front of it, what? You know what? This is what you can write down. Tyler pointed out, yeah, it is a tie. I would go, if you can go straight to there, great, but I walked you through the derivation. Friction equals what times what? Okay. mg parallel equals mu. What's this question asking me to find? What's mu? I don't know. What's mu with you? It's asking me to find mu. How would I get the mu, the coefficient of friction, by itself? Sorry? Oh, divide the normal force over. Okay. So if I hear you correctly, you're saying mu is going to be mg parallel divided by the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which force is the same size as the normal force? So I'm going to get mg parallel all over mg perpendicular. Okay. What was mg parallel? By the way, I think the m's cancel, and you could, if you wanted to, cancel the m's now. But I know some kids like to keep that mg parallel term and then say, oh, 2 lines is... Oh, you know what? It's going to be mg sine theta all over... Oh, of course it is. And the reason I kind of like this question is there an m on the top? Is there an m on the bottom? Well, hey. Whoa. What else cancels? What? Mr. Duick, what does that mean? It means that if you could somehow, using Star Trek teleportation, beam this ramp to Mars, where g is different, it would still stay at rest. Or if you could beam this to the moon, where g is different, it would still stay at rest. Or if you could beam this to Jupiter, where g is different, it would... In fact, if you beamed this anywhere in the universe where there was a different gravitational field, it wouldn't matter. This would still be the minimum coefficient of friction required to keep it at rest. So you've just found something universal, not just earthbound. But for a bonus candy, anybody know what sine over cosine actually is? I think in grade 12 this year you'll learn sine over cosine. It's actually tangent. This actually turns out the minimum coefficient of friction is just the tangent of the angle, which, since we haven't used tan for a while, we'll just do it the long way. So it's going to be sine 21 over cos 21. If you guys want to type that in, I'll convince you that if I go tan 21, I think I get the same answer as you guys that go sine 21 over cos 21. You need a coefficient of friction of 0.384. Units. Oh, no units. Why did I say minimum coefficient of friction? Well, it could be bigger. You might have to tilt this even further before you'd start to fall. But you'd need at least that on a 21-degree angle to keep your balance. I like example 8, I like example 8, I like example 8. Example 8 is a nice question. By the way, I don't see you till Monday. I apologize. You are going to end up with homework over this weekend or have to, but I don't see you for a while. It's because I did the little science-y demo at the beginning because I couldn't fit it in last class. Sorry. Why do I like this question? What's the very last thing it's finding? Well, what's C asking me to find? Time. What's D asking me to find? You know what? This one question is going to use the entire year so far. We're going to use forces, we're going to use ramps, we're going to use kinematics, we're probably going to use V and VI and VM and all that stuff. I like a question that lets me use the whole year. How would I start this question before I do anything else? How would I start this question? Yeah, and I'm going to draw mine up here just because from prior experience I know I'm going to need a lot of room. So I'm going to go There's my ramp. Here's the block. 32 degrees. What are the forces acting on this block? Get the audio going. Okay. And we're going to break mg up into components. We're going to break it up into mg perpendicular, mg parallel. I'll even put a little 90-degree right angle thingy there just to make sure I do the trig right. What else? Normal force perpendicular to the ramp. How big? The same length as mg perpendicular. About like that? What else? Is there friction in this question?
Yes.
Which way? Which way is this mass sliding? So which way is friction going to be? Yeah, which, you know what, really means this thing's going to slow down in a hurry. So I showed you it is possible to be sliding up and have no upwards force. It's just that it had its own momentum. Okay. A says, find the force of friction. Well, friction equals mu times the normal force. I don't know the normal force. Oh, but look, 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 look. Another force the same size as the normal force. Oh, mg perpendicular. Mg perpendicular. Which trig function is mg perpendicular? Now, by the way, if you blank on my stupid way of remembering, you'll notice, Ty, if you actually do the trig, if you say that angle and that angle are the same, and you label this, it is going to be adjacent, and hopefully that alone would make you say, oh, I think it's going to be cosine. Oh, cosine, if you blank out. So, of course it is, right? Mu mg cos theta. Now let's plug in numbers. Did I leave lots of room? I did. Okay. Friction equals, what's mu? 0.1 m6 g 9.8 cos theta 32. .1 times 6 times 9.8 times cos 32. And I get a friction force of 4.99, I guess, if I round off properly. Newtons. Yay. B. Justin, what's B want me to find? Oh, okay. Oh, for that. Oh, who's winning? Ah, it's a trick question. Who's winning? More than one winner, no loser. Most common mistake I see on this question is kids are so used to having friction be a loser, they put a minus in front of it. And actually, in this case, it's going to be a winner. We're going to get mg parallel plus winner equals ma. mg parallel. Two lines is sine. Plus, I could drop the 4.99 down, but I'm going to show you actually it's better to drop this algebraic expression down for friction, and you're going to see why in just a second. So I'm going to go plus mu mg cos theta. That equals ma. Can you see why I dropped the algebraic expression down? What cancels? The mass. What was I trying to get by itself, Justin? You know what? If the mass cancels, I've already got the acceleration by itself. I saved myself a whole line. So, is that a phone? I thought I heard a phone over there. Devin's trying to keep us straight. Colin's looking a little embarrassed. Is it Colin? No? Devin? Justin, Rob, or John? Oh, we're keeping the ear out. We want our Timbits, especially right before lunch. So, Lewis, I have no problem if you solve for friction first and then drop it down. Although I wouldn't drop down 4.99. I would drop down 4.986522 or 23. I'd carry extra sig figs. But you'll find actually it ends up being less work, even if you found friction already, because you would have found the algebraic version along the way to do so, to just drop the algebraic version down. Because now it's plug and chug. I mean, complicated plug and chug, but it's going to be 9.8 sine of 32 plus 0.1, 9.8 cos 32. I can do this. 9.8 sine 32 plus 0.1 times 9.8 cos 32. I get an acceleration of 6.024295. I'll write 6. You know what? Because I'm gonna use acceleration, I think, to answer C and D. I'm gonna carry some extra sig figs. 6.0243. And now I'll write it to 2 sig figs, or 3 sig figs. C. Quentin, what's C asking me to find? I'm going to go back to Unit 1. I'm going to use my DFIC approach. I'm going to say T equals question mark. Sorry, find time to what?
To stop.
Did you say stop? What else can I write? VF equals 0. Did they give me a VI? Yes? What? Oh, what did I find in part B? Ah! And I'm wrong. Can we see why? Yeah?
It's -6.
Are we slowing down or speeding up? So now we're back in Unit 1, where slowing down was always negative and speeding up was always positive. Now I've got to bring in my negatives and positives. It's going to be negative. I'm looking for an equation that has VF, VI, A, and T. Oh, this is the one we used all the time in Physics 11. This was the VF equals VI plus AT. It's going to be the T equals VF minus VI over A. 0 minus 20 all over negative 6.02. Now the nice thing is this, Devin, you know time is supposed to be positive. If you missed the negative in front of the acceleration, you'd get a negative time. Hopefully that would freak you out enough to go back and say, maybe I zigged with my signs somewhere. So there's a built-in little error check. 0 minus 20, or just negative 20, divided by negative, answer button. I get 3.32 seconds. What's part D want me to find? Oh, D wants me to find D? Yeah. I've talked a long time. I'm going to say I think we could handle it, so I'm just going to write D. We could find it if we wanted to. I'm losing you. I want to give you at least a couple of minutes to try this. There's 3 minutes left. I am going to, unfortunately, because this is the Physics 12 starting point, going to give you a lot of practice on this. So, (2B), but you can skip A. A says write the force equations. You're going to have to do that to find the acceleration, so just find the acceleration. 3 is good.
You skip 1.
I skipped 1. 4 is a lovely algebraic question. No numbers. It's saying, oh, if there's no friction, find an expression for the acceleration. You should find m's and everything cancel, and you just get g sine theta. 5 is good. 5 says how long, so it's saying find time. I got news for you. You're going to spend most of your time finding the acceleration. Just saying. Skip 6. I'm not going to ask you to find angle theta. It would be a shift sine or a shift cos question. It is kind of cool, but it's a little tough for what I'm going to throw at you. Skip 7, although it's lovely algebraic, I'm going to pass. Number 8, you can cross out A, but you can find B, force of friction and direction. Oh, look up. How about let's call this C and let's call this D so that you don't have part B, and part... Anyways, I'll fix that later. 9 I like. 9 says find the coefficient of friction. Find what's mu. I don't know. What's mu with you? Skip 10. 11 is fair game. 12 is cool, but it's finding an angle. But this is asking, hey, what is the maximum angle that a roofer could walk on a roof without slipping? They actually crunch this for like WorkSafe BC and things like that. So they actually do, but I'm going to pass. 14. And we'll pause there. That's a lot. But if you can butch your way through those, everything I do for my next couple of lessons should be... by the way, all we're going to add now is what if there's an Atwood machine, but on a ramp so part of it's at an angle instead of hanging straight down? Longer, not tougher.